right, thank you. Let's see if the network is back. But Lou, would you want to try to get this on online while I start lecturing? All right. Even the laptop's tired, I guess. Okay, today we're going to talk about output feedback. We might use the board a little bit more than I had originally planned. And if there's one thing that you absolutely take away from the lecture, is I want you to have a, let's say, upgraded view of what it means to be a controller, or even an optimal controller. You know, all controllers, but even optimal controllers are dynamical systems too. Okay, so I want to, you know, we've talked classically, you know, all of the conversations so far, we've been saying we've got some cost function, we've got some dynamical system, and we're going to come up with a policy u equals pi of x. Okay, and this policy is just a function, a static function of x. I'm going to mostly work over here. This is just my thing I want to leave on the board for the duration. And I want to upgrade to thinking now about my controller as taking in observations y and putting out commands u, but this controller itself can have internal state and is a dynamical system, just like all of our beautiful dynamical systems we talked about in class. And I really want to start thinking and give you the core tools about thinking about the controllers as dynamical systems today. And it's more motivated, of course, by the need to do output feedback. Okay, so you know, last time we went from our deterministic dynamical systems, you know, last week we were working with dynamical systems that gained some, you know, disturbance input. And we'll continue to do that now, but we're going to add one extra piece now, which is to start saying that we have measurements that come out of our dynamical system, which are going to use some other function, potentially, you know, arbitrary nonlinear function. It could depend on all these things. And this is also the output of some random process. Is it working? Yay, thank you. What did you do?
I just unplugged the router.
You unplugged the router. I'll take it. All right. Okay, so for instance, this could be to model measurement noise sensor miscalibration measurement unit in my buried somewhere in the robot over here, and I have to take potentially noisy observations from that inertial measurement unit to try to estimate orientation, accelerations, and the like. Okay, and that is a fundamental change to the way we're going to be doing control, and I feel bad that we got to almost the end of class without having mentioned it more. But many of the tools still apply or can be extended. Certainly the thinking can be extended. So that's the goal for today. Now, like I said, we've in dynamic programming, in optimal control, especially these additive cost formulations and the Bellman equation, the optimal policy was always representable as a static function. U star could, we gave up nothing by saying that my feedback controller is a function of state. The state is all you could know in the full state observations. And this is still true. Nothing's changed about that observation. What's changed, though, is in order to execute this optimal policy, I don't get to do this ideal implementation of the optimal policy because I no longer have direct access to X. Okay? So in order to apply this optimal policy, which is a function of state, I have to work somehow directly from the outputs Y. Now, of course, one of the things we'll talk about doing is how do you estimate X from Y, but actually that's not necessary, and it may not even be a good idea. Okay, so that's where we were before. So a natural first question. Why not just do U equals pi of Y? Right? What would it look like to try to optimize controllers that were static functions of the observations? Okay? And this is called static output feedback. So let's just work an example. Like what would that look like even in the linear case if I had x dot equals ax plus bu, we can add the noise or not, and y equals cx. Then it's interesting to ask, can you find me u equals negative ky? Right? The optimal policy we know is negative kx. Can you find me u equals negative ky? Now, of course, if C is the identity matrix, then there's no difference. So the interesting case is when C is Jack was joking about it, but when C is a low rank matrix, right? It's has less rows than columns, for instance. So maybe I only get to see if X is 10-dimensional, maybe I only get to see 3 of those states in my output, for instance. Or somehow if it's just, if it's low rank. If C is invertible, then these problems are equivalent, but if C is not invertible, then it gets interesting. Okay, so it turns out that there's, of course, a lot known about this problem, and I think it reveals, even this very simple version of the problem reveals some of the interesting things that happen when you switch from state feedback, right, to static output feedback. Okay, and there's actually a simple example that Jack used a bit when he talked about the the network's being a little funny here. Oh, there it goes. Okay. See if that does better. Okay. Sorry, my internet's giving me trouble, but this is my version of an example that Jack gave too when he was talking about when he gave the guest lecture on policy search. Okay, so x dot equals ax plus bu, y equals cx. To keep it simple, I've chosen y to just be a scalar. Okay, so the feedback here, actually, since u is also a scalar in this example, the feedback controller would just be u equals negative ky, where k is a scalar. If I were to think about the static output feedback problem for this particular matrix, k is just a scalar. Now the eigenvalues of this matrix, the thing that tells me whether this system is going to be stable or not, if I were to stick this back in, I can see that I can write the closed loop system dynamics as A minus B C, BKC, that's much better. Times X. That's just substituting this controller into those equations to get my closed loop dynamics. So I would expect this system to be stable if, for instance, the largest eigenvalue of this, the real part of this, is less than 0. Now, if I write a cost functions on it, like LQR or something like this, then I could ask, how do I find the best k by searching over the, searching over some cost landscape. That's what Jack talked about. But I'm going to ask even a simpler question: just which are the k's that are stable? Because any cost function I put on for k's that are unstable, the cost, any reasonable cost, is going to be infinite. And that's what this plot is right here. Okay, so this is a value of k. A handful of different values of k, and this is the largest eigenvalue of the closed loop dynamics. And what you see is that the set of possible stabilizing k's for static output feedback is a disconnected set. Okay, so very, very simple problem. If you just want to optimize over different k's, if you start your gradient descent algorithm, for instance, over here, and you're trying to look around for the best solution could be over here. And the way you have to get to it is you actually have to go through completely unstable, achieving infinite cost in most formulations in order to get back to this better solution. Okay, so there was a key result that Jack presented. He says for LQR, I can actually just do search in K. And even though it's not convex, it had no local minima. Do you remember that whole story where he showed things that were benign, non-convexity and the like? So for LQR, for instance, you can search in K just by doing gradient descent for full state feedback. For output feedback, it looks like that might not work. Okay, that we're going to have objective functions where you just can't get there from here without blowing up the system. So that's a simple example, but it's evidence. It's evidence that we got something harder going on here in this version of the problem. Okay, so optimization that's based on walking around in the parameters of K is harder in the static feedback case. Okay, that's just one observation. I mean, in many of the control design tools we've done in class, for instance, there are often like clever reparameterizations of your control gains, right? So maybe you don't want to search in K, you want to search in some combination of some reparameterization of K. But it turns out there's an important result by Blondel and Tsitsiklis, Vincent and Blondel and Tsitsiklis, which says actually finding, if you just even have A, B, and C as your data, then asking about the set of stabilizing Ks is actually NP-hard for static output feedback. Clearly for state feedback, it's not hard. We have good algorithms for it. We have convex optimization. But actually, in general, the static output feedback problem is known to be NP-hard. This is just the smallest, simplest example to give it some intuition about why it's hard. It's because the sets can become combinatorially disconnected even. Okay? So that's kind of disappointing. This seems like it should be a natural extension to go from here to here. But there's a chance it doesn't work. We don't have like the same linear optimal control sledgehammer for this version of the problem. Okay, and I've got the citation in the notes, and you should look at it carefully. I think that I want to be careful about stating NP-hardness results for something like this. I think actually maybe the field is fairly conservative. There's less results sort of in the space of static output feedback in control, let's say relative to its importance, probably because there's hardness results, and people know you're not going to get a magical solution to this problem that works in all instances. To some extent, though, I'd say reinforcement learning has come along, and people are like, let's just do gradient descent in this space, right? And it works sometimes. We know it's not going to work always. There's a hardness result saying that there are problem instances. There are values of A, B, and C that you can find for which the solution is bad. But that doesn't mean you can't very often find good controllers by searching in this space. And I think RL has taken a different approach where it works sometimes, and that's cool. And I think it actually reminded us maybe that we wrote off, like in fact, if you look at the systems that are the really bad systems, they're like, they can be contrived examples, right? They could be like these arbitrarily hard things that maybe nature never gives us the really hard things. So maybe there's actually something to be said for understanding a smaller class of systems that are not all possible matrices of any size, that could have any combination of poles and zeros, hopelessly intertwined, and make these problems bad. But on the cuff, the high-level observation is that there are hardness results saying that static output feedback is harder than full-state feedback. Is that clear? Did I say that well enough? You can do it. It can be useful. You can do it, for instance, with sums of squares, right? So if you want to search for polynomial controllers that satisfy some Lyapunov condition, right? If you had polynomial dynamics and polynomial output functions, then you could, for instance, sums of squares alternations right, you can parameterize, for instance, u equals k of y, where this is a polynomial function. And there's a lot of the advanced tools from class can work on this version of the problem. You just don't expect them to work always. That's the only thing we've lost, is that there's a hardness result saying there are going to be some instances of the problem where it's not going to work. Okay. So how do we do something different? A super important class of output feedback design are the observer-based feedback controllers. And this is the natural inclination that has been a mainstay of control for many years. It turns out, you know, the simplest forms of observer-based feedback are actually pretty simple. So you could take entire classes on state estimation. I'll just do the simplest form of observer-based feedback. Okay, so here's a canonical observer equation. So I'm going to use this as x hat is my estimate of x. Okay, so I'm going to make a dynamical system that tries to act like a state estimator. And a reasonable model for how that estimate could evolve is that it moves forward as if it's got the nominal model. I'm going to pretend W is 0. I'll be optimistic. But then it adds in a feedback term, if you will, which in the simplest case is just a gain. So this is a super interesting, simple equation. This is called the Leuenberger observer, family of observers. So if I had no measurements, then I would just be, I would have some initial guess at x hat, and it would just march forward. I would just be simulating my model forward, pretending there was no noise. And I would have some, just based on integrating those dynamics forward, I would have my model of x evolve. That wouldn't be very good. If I had even an initial error in my x hat, or if I had any noise, then those two are going to drift. This is a feedback term, which is saying this is the y I actually measure, and this is the y that I expected to measure if my state estimate was correct. Okay, and I'll multiply that by a matrix. Okay, that basically says that's trying to basically pull y and y hat together. Okay. Now you can see this very easily in the linear case. So if I had x dot equals, I'll just even do it without u, just to keep the writing smaller, simpler. If I design then my observer to be a of x hat plus L y minus cx hat, then I can actually rewrite that as ax hat plus L c of x, the true x, minus c of x hat. There's some noise in there too, but we're gonna worry about the average behavior here. Then if I think about the error coordinates for that observer, the error in the observer, which would be x hat minus x, then I can write the dynamics of that. I'll call this x bar. My error. And I get ax hat plus L cx minus cx hat minus the real x hat real x hat is, I wrote this twice, minus ax plus noise terms. And this works out to be A minus LC x bar plus some noise, which is the famous sort of observer equations. So the observer error is stable, will converge to 0 if the eigenvalues of A minus LC, if this system is stable. Okay, so that's a clever trick. It turns out you don't need to like try to invert C at any time or whatever. You can come up with a matrix L that if you can make this closed loop system stable, then you'd expect your state estimate to converge to the true state. And this gives you a way, if you know A and C, you can design an observer gain by searching or optimizing some cost function over the set of stable A minus LC matrices. Okay, it turns out, how do you design like I said, you can search over any of those stable matrices, but by far the most common way to, the most popular way to design L would be the Kalman filter. Which is an optimal filter, and if your system is linear Gaussian and you have quadratic cost. Okay, so the Kalman filter gain gives you the L that you stick into this equation. So hopefully, maybe you've heard of Kalman filters and maybe you've used them. It fits right into here. A Kalman filter is just an optimal Lüneburger observer. Okay, but the concept is more broad, and we could search directly in L with other objectives. We could search for it in a part of a bigger optimization. We're going to try to extend those ideas. Okay. Interestingly, the Kalman filter, if you look at the Kalman filter equations, some of you know them sort of from a different context, but they're very much, people say it's the dual to the LQR problem, but the Kalman filter equations are the solution to a Riccati equation, right? There's an infinite horizon steady state Kalman filter, just like the infinite horizon LQR, or there's a finite horizon time varying Kalman filter gains. All of the Riccati equation work we did for LQR, there's a very similar set of equations for the Kalman filter. Okay, it's not an accident, they're connected. In particular, they're connected in the case of LQG control. So if I want to minimize the expected value of my, let's say, infinite horizon LQR cost, all the standard stuff. So this is the stochastic LQR problem we did before, but I'm I'm going to add in y and say that I only have access to observations of y. Okay, that's just a statement of the LQG problem. It's almost exactly what we did before for the stochastic LQR, but I now have to do the output feedback version of it. And the amazing thing about this is that the solution turns out to be simple. Okay, so remember, if I have this cost and I have Gaussian noise, the cost to go is infinite. It had that form x transpose Sx plus a constant, which is growing to infinity. But the optimal solution turns out to be, and we'll do the derivation, but the Kalman filter followed by LQR. How many people know that result, have seen that result? Okay. So this is the number one result in output feedback, is to say that if your problem is a linear quadratic Gaussian, then actually the optimal thing to do is state estimation with a Kalman filter. You take that state estimate, and then you act, your policy, given that state estimate, is just the deterministic policy. That's a very surprising result. Okay, that you can actually design your control gains as if the system was deterministic and plug in this estimate x hat, and that's still optimal. It's a major result in optimal control. It's often called the separation principle. Which sort of justifies, in the linear Gaussian quadratic regulator sense, that you can design your state estimator, have one team, if you've got your autonomous car company with 150 employees, then you put 50 of them on your state estimator, and you put 50 of them on your controller, and then the other 50 are like, I don't know, lawyers, probably. Right? Maybe it's even 10, 10, and yeah. Okay, so that's a major result. One thing that I have to say, right, that you'll hear control people say often is that the separation principle holds only for linear Gaussian quadratic problems. It does not hold, well, there might be other problem instances where it holds, but it does definitely not hold in general. Okay, so when engineering teams are working on Atlas or autonomous cars or whatever, we still tend to separate the state estimation team from the control team, but that is not fully justified in the general sense. That's an approximation. And to plan deterministic control and feed it just your best state estimate is not guaranteed to be optimal in any way. It's a heuristic. Really, yeah. More generally, like you could think about having y come in. You could have your optimal Bayes filter. I haven't even said what a Bayes filter is, but you could have some sort of optimal filter in a Bayesian sense, okay? And you could send that to a controller. That diagram's okay, but the thing you have to pass across is an entire estimate of the distribution over possible states. okay? And the controller needs to be something that, in general, is designed taking into account the entire distribution or statistics of that distribution. The surprising thing here is that these gains could be designed as if that was the true x. And the other surprising thing, you would think in LQR that you would need it to pass the full Gaussian distribution. You'd think you'd need to pass the covariance matrix too. But actually you just need to pass, in LQR, you just need to pass, in the steady state case, you just need to pass x. Okay, but in the full glory, you need to pass the full state of Smith. This is where people talk about like the belief state planning, information state. And it's not really, I'm saying this so you can connect words that you've heard and make some connections here, but that's not really a deep observation in some sense. It's, this is just, this estimate here is basically a sufficient statistic for everything that's possibly been passed in, right? I could take out an entire history of y's and represent it in there with no loss of information, okay? So it has to be sufficient for optimal control. Okay, so here's an example of how you would use this sort of observer design in practice, for instance, on an underactuated robot. So I coded up an LQR, or an Acrobat example. So Acrobat balancing are one of our standard problems, okay? But from only using the encoders. So I'll say only position sensors. Okay, so my Acrobat plant here is my normal system. I have U coming in, I have X coming out. In order to use the full glory of the Kalman filter and everything here, I went ahead and added some exogenous noise input into my Acrobat. And then I have a little system in Drake that models rotary encoders. I can, that system can model quantization effects and other things, but and could probably be richer than it is. But so I have a system that's somehow taking this and then outputting my measurements y, and it's effectively implementing something that's just selecting the first, in the simple case, scaling and stuff based on the encoder parameters. But for our purposes, think of it as taking my four-dimensional state and picking out the thetas, possibly scaling the thetas, okay? And not giving me direct observations of velocity. Now, of course, if I watch that over time, I can do temporal differences to estimate the velocity. But I don't have to do that explicitly. The Kalman filter design is going to do the work for me. If I've designed an observer that satisfies those equations, or is it optimal in some sense, then it will recover the velocities as needed. So I pass this into a Kalman filter. In most control packages, there's a linear quadratic regulator function, there's a Kalman filter function that will give you the Kalman filter gains given the model of the plant and the covariances of the process and measurement noise. And that gives me x hat. Okay, and then I pump that back through my LQR controller to get my U. And I have a couple loggers in there and stuff too, and a visualizer so I can see what happens. And it definitely stabilizes the true acrobat. Of course, this is what we had to do on the real system. And it's also meaningful to track the estimator error, right? So these are small numbers, but the Leuenberger observer with optimal gains here will have error initially in the estimate of x, but it quickly not monotonically, but it quickly has a stable linear system response that drives that error to 0. Okay? Small fluctuations around the 0 because of the noise. Does that make sense? Yes.
So can that error before it decays cause the system to act unstably? The error in estimation.
Awesome. So the question is, can this error in estimation, like that looks a little scary that it's going up before it goes down and everything like this. Can it cause the system to go unstable? So for a linear system, no. But once it's a nonlinear system, then yes, it could be certainly that your initial deviations. Now, if I were to do it without state estimation, you might still see you will in the Acrobat still see a non-minimum phase response. You'll see it going away in order to come back. That's the requirement in the Acrobat dynamics. But this is exaggerated, for sure. Yeah, so that's a question I wanted to ask actually. Is so what in general would you expect of this performance of this system compared to the full state feedback controller? Right. So you're pointing out that it can go away before it comes back. What else would you worry about? How would you compare those two systems? X hat is going to converge to X, but there's always going to be some lag, some delay, appropriately. So the system response cannot be as aggressive or as fast in the state estimated version, right? A linear filter will necessarily add some delay to my system. Okay, so the truth of the system that you have to implement is not quite the deterministic one, okay, and the performance will be subjectively less. How many states are in this diagram? If I were to like make a diagram, say number continuous states for this diagram, how many states are in this diagram? 8. Yes. Right, I get 4 from the Acrobat. And 4 more from the state estimator from the Kalman filter. Okay, so the satisfying answer to your question, I think, Cole, is to say, what is the region of attraction of the system, which we could do with Lyapunov and sums of squares. But the system under test is not a 4-state system with just the Acrobat dynamics. The system under test now is an 8-dimensional state space with the dynamics of the Acrobat plus the dynamics of the observer. That is going to have an ellipse, ellipsoidal approximation of the inner approximation of the region of attraction. And I would expect that if you were to project that region of attraction in 8 dimensions down into the 4 dimensions, that it's going to be a little bit smaller than the original one because of those delays, right? And potentially, I mean, the delays are a way that you might have to deviate. Does that make sense? Yes?
If C is sufficiently low rank, then obviously you cannot do control. So how do you get a sense for when you can do control?
Great question. So you're asking about the sufficiently low rank. If C was all zeros, it's not going to go well, yeah? So in the linear system case, it's the same way we could test for controllability. You can test for observability by asking questions about there's an observability Gramian. It's using this A minus LC logic. And you can pull that apart and ask a question, is a system observable? Is C sufficient to accomplish a task? And then the condition number, that will talk to you about how quickly you could converge roughly. So all those questions are relatively easy in the linear case, right? In the nonlinear case, then you have to invoke stronger tools, and in general, you might have to be optimizing over L to answer a question for is the system, finding a stabilizing observer might be the way to answer a question about is the system observable. There's special cases where you can know that it's observable, even in a nonlinear case, if it has certain properties. But certainly, C can be far from, so oftentimes, as long as, observability is a much different condition than full rank, right? They're very different conditions. You can have a small subset of your states observable, directly apparent in your outputs, but as long as the dynamics are coupled, right, then things are going to work. So for instance, if I had like one pendulum on that table and one pendulum on this table, and I had only sensors on that table and no sensors on this table, right, I could have the same size matrix here, but that's not going to be observable, right? The dynamics, the reason that I can get away with this is that the dynamics couple the missing observations. Yes?
You can also have a case where you have more noise measurements, right? So higher dimensionality than like when you use like a gyroscope and a magnetometer or something to estimate an angle.
Yes.
So like that would give you a faster response like this than in your like Kalman calculation.
Okay, so super good. So you're asking about, so like what about the magnitude of the noise, for instance, right? So, but what was the conclusion there? Was that?
Yeah, like the other question is, so sometimes you have more noise measurements. So
Yes.
You have, like you're trying to estimate angle and you have like an accelerometer, so you have like a gyroscope and a magnetometer, so you can sort of like do both.
Correct. So in the linear case, the magnitude of the noise won't affect whether the system is observable or not. But the Kalman filter will help you balance those, right? So if you say that one measurement is very noisy, the other one is not noisy, then it'll put more weight on the clean signal, right? Weighted by its importance through the coupling of the dynamics. So the Kalman filter is exactly the right answer to that idea, which I think you understand, yeah. Great. Okay, so to keep going, like to close the sim to real gap, if you will, the modeling to real gap, there's a bunch more things that I would want to add to this model. Some of them are easy to take into account with observers and control design. Some of them else are not, right? So the encoders almost always have calibration offset. A lot of robots these days are like, certainly like Atlas and some of the other humanoids, they kind of wake up and they go to their joint limits, which is a known configuration. They zero their encoders and then they come back. You kind of wonder why the robots will stretch, but they're just trying to zero their encoder calibration, right? And then they come back and then they slowly slip out of calibration as you move them, and the better robots slip less out of calibration. There's quantization effects that happen, right? Because encoders typically have discrete ticks. So you're actually not measuring a continuous value of theta, but you're measuring some quantized value. The bigger ones, though, are actuator backlash. And actuator stiction. Okay, those are a real pain in the Acrobat. And if you look carefully at the balancing, oh, that's so low frame rate, but okay, so look, it's balancing, but it's not deadpan on zero. It's going to walk around a little bit like this forever, okay? So that's because of backlash and friction in the actuator. The backlash we tried to minimize. We actually used a non-standard belt drive in there, basically, in order to try to minimize the backlash. Okay, but imagine if you're exactly upright, everything's good. If you're just a little bit off, okay, and you apply a little bit of torque, but you're in a friction regime on your actuator, then a little bit of torque accomplishes nothing in terms of moving the arm. So you start falling until you get enough torque that you break through friction, and then you move over, and then you end up doing this little dance for the rest of time. okay? You know, backlash is similar that with gears. If your teeth on your gears are aligned on one side, then you're able to instantly apply force in one direction. But in order to apply force in a different direction, you have a moment of not applying force before you apply force and make contact with the other side of the teeth. That's the simple example of backlash. You can model that as a hybrid system with contact and do the work there, but there's not great solutions actually. I mean, you're still going to have to think about that, the discontinuity, and it's very hard to do fine-grained control on an unstable system in a backlash and frictional contact regime. But the trend is here that I want you to understand is that, you know, the more modeling you do, then the higher fidelity your control can be, and the higher performance you can get. You can probably get things to work with pretty sloppy models. And if you dial in more accurate models, then you might be more sensitive to model errors, but you can ultimately, you know, achieve higher performance, right? So if you're a household robot and you're just trying to, you know, fold the laundry or something, maybe you don't need super high precision, and maybe we won't ever get it for laundry. That's a pretty hard modeling problem. But if you're like, I don't know, the Millennium Falcon trying to, you know, split the uprights, right, as the doors are closing, you know, then, and you need to be dead on with your dynamics dialed in completely, then, or the quadrotors that were flying through hula hoops or whatever, you know, that's where you want to have a higher level of modeling accuracy, and you can get higher performance out. Okay, so this is one view of control, okay, which is that I have my dynamics over here and my control gains over here. But actually, the more general view that I'd like you to have is this view that is the major takeaway for the class, is that this is a dynamic controller. Right? So the states that are in the Kalman filter are really just part of this control system. Think of this control system as having states, 4 of them for if it's got a state estimator for the acrobot inside it. Okay, and I can think about this as a dynamical system, which I might write as having some state of my controller. And maybe, you know, I'll just write it like this. And the sort of more general view of this is that I've got some design problem where I want to build a dynamic controller here. By searching over the dynamical system parameters, if it's a linear dynamical system, I can parameterize it with these state space matrices, AC, BC, CC, DC. Right? Those are the states of the controller. In the Kalman filter, the state of the controller happened to be the same size as the state of the plant, and that's important, okay, for that result. But more generally, there's nothing that says that that must be the case, right? You could have 2 states here and see how well your system could do if I could find good A, B, C, D matrices in order to try to stabilize the acrobat with control gains that were parameterized with a 2-dimensional, you know. Or you could try to go into the over-parameterization regime and make this like 1,000-dimensional, right, and see how that goes, okay? There's an interesting search problem of saying, how do I search over the set of dynamically stable controllers, of dynamic controllers? Right, and of course there's an equivalent. So in the Ludenberger of case, for instance, then this just as AC was A minus LC, for instance, and I could populate those. That's just a different way to write, you know, a more general way to write the system. Okay, so the next question I want to ask as we're leading to, right, so the LQG is kind of a niche way to compute those parameters, can I ask the more general question of like, search for AC, BC, DC in order to find a good controller that minimizes some objective? Okay. The answer is yes. With an asterisk. With some caveats that I'll try to be clear about. Okay, it turns out, just like for LQR, there are some clever parameterizations that take the problem that was non-convex in K and turn it into a convex problem in a higher dimensional space. The control theory as a community is just very smart, right? And somebody out there figured out a way to write a convex reparameterization of this problem, right? That can, for LQR objectives, H2 kind of, or H infinity objectives, there are convex reparameterizations for that problem that allow you to solve for AC, BC, DC given objectives, for instance, for LQR, H2, which is the noisy case, or H infinity type problems. And there'll be references in the notes for sure. Maybe the whole equations will be typed out, but they're actually not pretty. The convex reparameterizations are these kind of mess of equations. Okay, but there's a caveat. So what is the caveat? There must be a caveat, because certainly if this was true in its full generality, then you could ask for trying to solve for these in the case where the dimension of AC, the dimension of my controller, was 0, which would be the static output feedback question. The static output feedback would be a limiting case where I just set the dimension of x to be 0, of xc to be 0. So clearly, it can't work for arbitrary choices of matrix sizes AC, BC, DC. There's got to be something else. It turns out this holds, they work when the dimension of xc is greater than or equal to the dimension of x in the real problem. And like if you're looking at the derivations, then in the convex parameterizations, the reparameterizations, there's actually a rank condition in there in the reparameterizations, which is a non-convex constraint, but it becomes trivially satisfied once this condition is satisfied. It falls away from the problem, and then you get a convex parameterization. So nothing I'm saying here is saying P equals NP or anything like this. But for the special case where XC is at least as big as the state and can have an interpretation of being a state estimator, then these designs can be done with convex optimization. Just like what we've said before, like for LQR, you don't need to solve a convex optimization. You can just solve a Riccati equation. That's a good way to get LQR gains. It's better than calling a semi-definite programming solver. The semi-definite programming formulation is more general. So if you want to do things like add extra constraints to the problem, combine objectives, then these convex reparameterizations can offer more generality. They also, Jack didn't actually, when he was talking, he didn't tell you about his latest results, but because they're an output feedback kind of result. But they also shed some light on sort of when gradient descent can work for these parameters. Okay, so and this is a super interesting question. Again, this time, not because I ever want to design, like I have better ways in the linear system known model world to design those matrices. Okay, but if I can show that gradient descent actually works on this problem, then that makes a connection to reinforcement learning, for instance, and to broader applications that maybe I can find these matrices with less or even no model. So one of the big questions that I think is essential for us to be working on, and a number of people are starting to work on, is you take some of the theoretical controls, the theoretical machine learning, and some of these applied successes in RL, and try to ask, like, when does policy search work? When, does it work? Jack did tell you about it working for state feedback. So now I'm asking, does it work for output feedback? In this case, where we already know there's good results from convex optimization. Can you search directly? If I just did gradient descent in that, would that have solved the problem? It turns out it does not work. Not in full generality. There are problem instances, plant models, for which that system, that optimization will have local minima and will get trapped in local minima. Okay, so I have some, there's a nice example from Li Na, who I think captures it nicely. Again, a very small linear dynamical system, a quadratic regulator objective. You start searching in the space of feedback, of output feedback gains, LQG gains, and the cost landscape here. This is a slice through a high-dimensional cost landscape plotted over some interval, and just to show that it has actually a stationary point, a saddle point here, which is non-optimal. So your gradient descent will get stuck here. And there's some, this is 2021. Jack's got a paper from this year that adds a little bit more. It talks about there's actually, Jack's result talks about you can add a small regularization term to the objective and then make it so it does work for the Kalman filter case, but we don't quite have the LQG case. It turns out a small tweak on the original cost function can make everything work again for part of the problem, not for the whole problem. But this is a frontier of what's happening, I think maybe theoretical RL and controls, right, is somehow trying to ask, like, when does this guarantee to work? When does it not work? Simple examples are shedding some important light. Okay, so that's like some basic understanding of sort of what we think about with output feedback. But I really want to make a point that the view of output feedback as state estimation plus control is it's very classical, it's powerful for a lot of things, but this is, I think, the thing that is falling down in our most exciting control applications these days. So it's a strong assumption to say, I need to estimate the full state of my world in order to make my control decisions. This is actually why I'm excited about manipulation these days, because it's forcing me to think about these harder problems. And I only have, those of you that hear me before, I only have like 4 favorite examples or something, but one of them is buttoning my shirt. Okay, so let's say I want to write a controller to button my shirt. And I've got some feedback sensors in my finger that are going to feel my button, feel maybe where the hole is, do their thing, right? I can button my shirt pretty effectively. I did not need to estimate the full state of my shirt in order to make those control decisions, right? Like the full state of my shirt, there's something going on back here, there's, it's some infinite dimensional partial differential equation. I didn't like start by estimating the full state of my shirt in order to make these local decisions. And there's countless examples of places where full state estimation is not required to make good decisions. And now this is maybe the case where, where these matrices are small, for instance, or at least, or the information is obscured, right? Maybe I can't possibly see what's inside my bag, but I could reach in there and have a pretty good controller for getting the pencil out, okay? This is the super interesting part of output feedback. Even when I was working mostly on legged locomotion, I was saying, like, the conversation I had with my students often was like, we're too dependent on state estimation. We need to be thinking about output feedback. I would say this constantly. They'd be like, I have no idea what you're talking. I mean, they knew what I was talking about, but they're like, I don't believe you. I can write a better state estimator, and we can make our walking robot work better, right? And it just somehow never. I mean, I think they probably believed me, but we never did it. There was always a better way in legged locomotion so far. I still think in legged locomotion, to get to the next level, we're going to have to rely less on full state estimation. But for me, changing to manipulation forced the issue. I say make some pasta. Like, what's the state of the spaghetti? That's just like a non-starter. You just don't ask that question. You can't even say, what is the state I'm trying to estimate, okay? It's a silly example, but it forced the issue. And it's now, I think there's a lot of people thinking about this. There's people thinking about it in the context of learning state representations from machine learning, right? And this is kind of, I think, what's happening well. One of the good things that's happening in RL is that they can eclipse some of the problems of state estimation by just searching directly in the parameters. So let me just try to connect those dots, okay? So what does it mean to search directly in the parameters of AC, BC, DC? That's, I hope, kind of clear in the linear dynamical system sense. And I just want to make sure you realize that that's, I think, exactly what's happening in the reinforcement learning, deep learning sense, without having told you in great detail about RL. I think I can still make this point, which is that for linear dynamical systems, which is how I'm going to represent my controller, there are state space descriptions of that, for instance. This would be like the state space description. But there are other descriptions too, right? So you can also represent a linear dynamical system with, for instance, an autoregressive model, or these input-output models, where you could say, for instance, this is A0 of yn minus 1 plus A1 yn minus 2 plus, plus B0 un minus 1 plus B1 un minus 2 without any explicit state. Just these are called autoregressive, ARX. That's a silly name in my mind, but autoregressive with exogenous inputs. These are, swappable. You can go from one to the other descriptions of linear dynamical systems. Okay, if you look at the neural networks for control, you will occasionally see static neural networks. You might see, for instance, U equals pi neural network of Y. That would be equivalent to, static case. But you'll often see the state space, which would be an LSTM model, for instance. We talked about LSTMs before, or recurrent networks. Right, the recurrent units are a state space model. They have their own state, and the state of those internal neurons, if you will, are representing a state space model with neural network equations. Right? And you'll also see people write a neural network that's a function of previous observations, for instance. Possibly autoregressive. Okay, and this is the ARX description, where you take a feed-forward network and you pass in a history of observations. Okay. If you don't autoregress in here, sometimes you can just do a history of observations, then that would be, I should leave this one here because that's perfect. I don't mean to say that that's not a good model. That's a great model. But you could have an alternative here, which is only with the functions of y and no u's. And this would be, again, this is just a limited form of the models. This would be a finite impulse response model. Okay, so when people are doing deep imitation learning or deep reinforcement learning and they're training neural networks and they're changing the parameters of the neural networks and they've chosen either recurrent networks or these histories of observations, which again, you'll see people go back and forth, right? You should think of that, I think, as doing search in the space of dynamic controllers that can represent, a dynamical system for the controller. It might try to estimate the full state, but there's nothing explicitly asking it to. And the interesting case is when it doesn't have to, when it's estimating much less than the full state. Is that analogy kind of clear? Now, we don't know when it works. I mean, like I said, we're at the frontiers of the current, front, like the battlefront of what we're trying to understand rigorously is like, okay, in the limiting case where you have a linear neural network, which puts me back into this, and I do search in the parameters, does it work? And it turns out, for some simple objectives, it doesn't always work, right? With some little heuristics, you can make it work better. Maybe those things we learned here will improve what we can do over here. Right? I think in general, I think this is shown in great success in some applications. I would like it to be more efficient and more well understood. We want to build it into a technology. And it may be that this is too simple, or it may be that this sheds some important lessons that go back and forth. Okay. So there's one more big idea that I won't do, but I have in the notes already, which is about another way to parameterize your controller that's good for output feedback, but for another day. Okay? So the optimal controller in the output feedback case is a dynamical system, right? Think about it like that, please. And I really think, I almost regret in waiting until the end to class. I think there's so much to learn and so much to build on, but I think the problem of our day and the reason that people think RL solves problems that classical control doesn't is because of the output feedback problem. And I actually think we should be understanding why RL works and understanding the model based in the output feedback case and bringing those two together. That's how we get everything better. Questions at that level? Yes?
How do you know if the
Yeah.
such a black box?
Yeah, that's a good question. So how do you know what the neural network is estimating, if it's estimating the full state or not? So there's various practical answers to that. One thing that people do is they do these linear probes, for instance. So you could say, maybe you know the state, for instance. You could ask, can I train a linear map from like a middle layer of the network, from the recurrent units, to, for instance, the state of the chalk, whatever. And if that would be a way to test, is this information that I'm looking for present in the middle layer of the network, for instance. And you do these linear probes to sort of go in and ask. Yeah, I think that can work. It's a weak question to ask, but. Okay, I'll hang around if people have questions with projects. Happy to answer them. And we'll see you on Thursday.